Hey.
What's up, Sagar sir?
Hi, Dilip sir. Very good evening.
Very good
Yeah.
morning to you.
Yeah, very good evening to you.
Yeah. How things going?
Yeah, going okay. Everything smoothly.
Yeah. Hopefully we'll have a great day today. Yeah, because Professor Krieger will talk about everything.
Yeah,
Research,
yeah.
writing the paper, it would be very much useful for the student, young faculty. I think that would be good. And because he has a very much experience as the department chair, as
Yeah,
well as
yeah,
he is currently serving as the associate dean for College of Science.
yeah, yeah, yeah,
So
yeah.
he has a vast experience. He was also faculty in the University of Indiana in Bloomington. So his academic journey will teach lots of stuff where you can learn. How the Zoom is doing over there? Is everything is okay?
Yeah, everything is okay today. Yesterday we
Okay.
faced some problem.
Yeah, you told me.
Yeah, yeah. Especially in the inaugural session. Later on, the session okay, was okay.
While you and I, Steve, were talking, maybe the Zoom became freeze, I think.
Yeah, yeah.
Then I reconnect again.
You unmute. Who is that making sound? Ask.
So the talk will start at 10 o'clock, am I right?
Yeah, yeah. What is time right now in US?
Uh, ours is 9:54, still 6 minutes to go.
6 minutes ago. Okay.
I'll also attend Professor Rao talk.
Hmm.
Yeah, that is on, I think, Sunday. I think it can sometime Sunday, yeah.
Good morning, Professor Deligar, sir.
Sir, very good morning.
Yes.
Good morning. How are you today?
Fine. Professor Anubule, sir.
Yes, sir. Fine, sir.
I hope I can start you all off with an interesting lecture, and you can be inspired all day, and I will go home and go to bed. So
Yes, sir. Yes, sir.
I'm actually already at home. I'll just go to bed.
Yes. Thank you very much, sir, for your valuable time for us.
You're most welcome. I'm happy to do it.
Yes. Thank you, sir. Thank you, sir.
Sure. So I have never visited India before, but now I can say at least that I gave a lecture at an Indian university.
Yeah, sir. And sir, yeah, okay. After every 3 years, we are organizing international conference, and okay, probably we are planning to organize international conference in 2022.
Yeah, okay.
Definitely, at that time, okay, we will plan to invite you for the international conference.
Yeah, well, it'd be lovely. Hopefully we can all travel then. So
Yeah.
Yes, sir. Yes, sir. Yes.
we all need to get vaccinated.
Yes, yes.
You see. Thank you.
If everything goes well with the pandemic, maybe we can invite to Steve to India.
Yeah. Definitely.
We'll give a tour of Taj Mahal also, 7 wonders.
Yes. Oh, it'd be wonderful.
Yeah.
So, Steve, can we start?
Yes, I am ready.
Very good morning to the Indian participants, and Very good evening to the US participant, especially today's guest, Professor Steve, my friend Dr. Dilip, and other participants from USA also. Then we are in the second day of online lecture series, which is organized by Department of Chemistry, Shivaji University, Kolhapur. And in this second day session, we have eminent the speaker from United States of America. Then I take this opportunity to introduce today's speaker. Today's speaker is Professor Stephen Edward Krieger. Uh, Presently, he is working as Associate Dean, College of Science, Clemson University. So he started his professional experiences, especially teaching and research experiences in 1987 at University of Texas. After that, he shifted to Indiana University, and there he worked as assistant professor. Then 1995, he had joined the Clemson University as assistant professor, and after that, in the various capacities, he is working in the Clemson University. After assistant professor, he shifted to he promoted to associate professor in 1998 to 2000. 2000 onwards, he is working as a professor. Then in the period of 2007 to 2013, he worked as a departmental chairman in Clemson University. Then in 2013 to 2014, he was provost fellow in Clemson University. Then he has worked also director of space optimization College of Science in Clemson University. So he has huge experience about his professional career. Then as concerned to his education, he completed his BS in chemistry in one of the reputed institute from the United States of America. Then he also completed the PhD from University of North Carolina. Then he has also he has been working with many of the professional bodies. He has been working with the International Society of Electrochemistry, American Chemical Society, the Electrochemical Society, the Society for Electroanalytical Chemistry, then American Association for the Advancement of Science, Sigma, XI, Scientific Research Society, and many others. Then that's known is the professional and research credentials. He has been awarded with many honors, especially the Clemson University Research the Scholarship and Artistic Achievement Award in 2019, Crystal Flame Innovation Award presented at Fuel Cell South 2004, which is given in the conference in Columbia as C2 team of Krieger, Smith, and et Then he has also awarded with the Faculty Excellence Award by Clemson College of Engineering and Science. And then he is also awarded with Ely Lilly Analytical Chemistry Award in 1992, and many other awards to his credit. Then he is also associated with the many journals as a editor as well as the associate editor. Then as concerned to his the research credential, so far he has published more than 160 research articles in the international journals. He also published many book chapters as well as the different articles in the conference proceedings. Okay, many patents related to his group. Then, as concerned to H index, his H index is more than 40, and the citations are more than 10,000. So, okay, we are going to a huge biodata, but because of the time constraint, I have highlighted the few things. And once again, I welcome to the Professor Krieger. And I am also welcome to Dr. Dilip, and Dr. Dilip is my best friend, and he's one of the collaborators of my research group. And he has actually, I requested to Dilip about the few speakers from the United States of America, and immediately he contacted to the Professor Krieger and Apparao. And because of Dilip, today for today's session, we have the Professor Krieger as one of the speakers. So once again, I'm welcoming to all the participants as well as the speaker. And may I request Professor Stephen Krieger to take the charge and proceed further. Thank you.
Very, very good. Thank you. Thank you for the kind introduction. And I'm very happy to be able to speak with all of you this morning. Good morning to everyone. I said a moment ago, this will be my first time speaking at an Indian university. Unfortunately, I didn't get to visit India at the same time, but that's okay. It's still very delightful to speak with all of you this morning. Dilip asked me to prepare a talk on scientific writing. So that's what I have for you this morning. This is not really a research talk. That would be a different talk. I'm not going to give a talk on my research. I'll talk a little bit about some of the things that I've learned and some of the advice that I would have on scientific writing. So perhaps that will be useful to some of you as you are writing. And I'll tell you a little bit also about Clemson. And I think the next thing I need to do is to share my screen. And so I think you can all see my screen now, right?
Yeah. You go for a slide presentation. Yeah.
Good. Okay. Well, let me move this over here out of the way. Okay, so my talk is on scientific writing. I am a professor of chemistry. I didn't write that here, I should have. I'm a professor of chemistry, and I'm the associate dean in the College of Science at Clemson, which I enjoy a lot. Our college is relatively new. It's been in existence about 5 years. It brings together physics and chemistry and mathematics and biological sciences. And I'll say more about that a little bit later on. But I'm very happy to tell you a little bit here today about Clemson and about some scientific writing. So, yes. And
Bluetooth बंद करना चालू कर आवाज ये ना
so, and it might be good if everybody were to turn off their microphones so that that'll make it easier for everyone to hear. So you may wonder where Clemson is. This is the United States, and this is the state of South Carolina. Clemson is here in this northwest corner of South Carolina. So we're about 120 miles from the large city of Atlanta, maybe another 120 miles from the large city of Charlotte. Kolhapur, India, a mere 8,575 miles, long ways from you. But that's where we're located in the United States. This is our main building. This is our founder, Dr. Thomas Clemson. He's a chemist, in fact, founded the university. So these are just some sights from around our area. We have a lot of natural beauty, some small mountains, some waterfalls, some beautiful flowers. This is a group of our chemistry graduate students. So some of the things that we do some fun rafting trips on rivers and do some things outdoors. So we have some good group activities with our graduate students. This is not our whole group. We have about 100 graduate students in our chemistry department at Clemson. One thing we're known for, you may have heard of, is American football, not to be confused with European or football in the rest of the world, which we call soccer for some reason. But football for us is this, and this is our stadium, and it's a lot of fun to go and watch a game. So that's Clemson in a few words. So if we want to think about scientific writing, then I think it's useful to think about scientific information. Okay, so scientific information really is what we write when we do scientific writing. And so, and I wasn't sure if this was an audience of chemists or not. It is, so you all think like I do. So if you're a chemist, then you might think about chemical information. You know, what's the simplest thing that you might think about? Maybe measurements, maybe a property. You measure a boiling point of a liquid or a melting point of a solid, or maybe a color of something, or maybe a viscosity or a density. And you could go from this less sophisticated property to maybe something a little more sophisticated like reactivity. You know, you can measure the density of sodium metal, and then it's a little more sophisticated to think about sodium metal maybe reacting with water and making whatever the products are. There are some other ways to think about the sophistication of scientific information, and that is maybe you go from properties to structures. So you can easily measure the density of water. That doesn't tell you the structure of water. The structure of water is a more sophisticated topic. You can understand basic aspects of reactivity. And then if you use your knowledge of reactivity, then you can do a directed synthesis. Okay, so these could be thought of as more sophisticated pieces of information. And if you do enough of this type of research, then your knowledge of properties and structures and reactivity and many, many other things can all come together and allow you to come up with some principles. Okay, and so you might find a textbook, for example, that might be titled Principles of Chemistry. That was the name of the textbook that I used in high school. And so this collects together a lot of knowledge. And when you have a lot of knowledge, when you have principles, then you have this very powerful ability to make predictions. And when you can make predictions, then you can engage in design. So you could not just understand that water has a boiling point of 100 degrees Celsius, you could maybe think about, you know, how to use water for something, how to change the boiling point, maybe at different pressures, maybe by adding salt, or maybe understand how the boiling of water affects the behavior of a volcano. So you can become more sophisticated in your understanding. So that's one way to think about scientific information. So where does all this scientific information come from? Well, over thousands, you know, certainly tens to hundreds, maybe thousands of years. There's been a lot of research that's been done, but you didn't do any of that research, right? You all read about it somewhere, or you heard about it somewhere, because it's all been recorded. And so what are the different ways in which scientific information is recorded? Well, we can think about what we would call a primary source. So if you're a research scientist and you want to write the results of your research, that's maybe what many of you might want to do, then you might write a journal article. We'll talk more about that in a moment. You probably all know what that is anyway. You could imagine that your primary information would be contained in journal articles or project reports, or maybe a patent. Sometimes books will be published that will contain the original data. Most often books are more like secondary or tertiary sources. So you take results from a lot of articles and you put them together in a book, and you don't put necessarily all the articles in the book, you put the principles in the book that came from all of those articles. So when you're a college student, or even a student at any level, you will often use textbooks and handbooks and things that are collected information. But all of the information that's in these textbooks and online sources as well, it all comes back to these original journal articles. That's the primary source where we record scientific information. So scientific information, you know, published in journal articles, this is the mechanism by which we usually, sometimes if you work for, let's say, a company and you don't wish to disclose what you've done in your research, then maybe you put it in a patent application, or maybe even in an internal report. If you work in a university and your goal is to disclose the results of your research to the public, then you would very often do this with a journal article. And most journals, many of you have probably found many journal articles, even in no matter how long you've been studying as a chemist. Many of these journals are published by professional societies, such as the American Chemical Society or the Royal Society of Chemistry or the American Association for the Advancement of Science. There are Indian associations as well. This is not obviously a chemistry society, the Institute of Electrical and Electronics Engineers, IEEE, but they publish a lot of journals across a wide range of areas. And this is just a selection. There are many, many, many societies, and there are also professional or dedicated science publishing houses. The journal that I'm an editor for is called the Journal of Power Sources. It's published by Elsevier, which is a very large publishing house, publishes journals across many, many, many different disciplines, including electrochemistry. They're not a science society, they're just a professional publisher. And so journals, long ago, if you maybe got a journal in a paper copy, then once a month or once every 2 weeks in your mailbox would appear a journal, and it might have a nice cover like this. You think of it as a magazine and you can read through it. Very few of us do that now. We almost all get our journal articles from electronic sources. Nonetheless, the journals often still have covers, and if you are a really clever artist, you drew something like this, then you can get your art put on the cover of the journal, and maybe somewhere somebody gets a paper copy of this journal, but most often people access these types of things electronically. So just got a few interesting little things to tell you about journals. Maybe you know some of these things already. A scientific journal will usually have an editor, and there might be an editor-in-chief, and then also a group of editors who work with that editor-in-chief. And those are the people that are in charge of the content of the journal. And in many cases, journal editors are people like me or professors. So I work as an editor for the Journal of Power Sources. I receive a little bit of pay for that, not very much, really. Many journals, you receive nothing for your pay. It's just something you do as part of your professional responsibilities. The manuscripts, so this is a very different business model, shall we say, than say, Time magazine, right? Or the New Yorker magazine or something like that. In other types of magazines, manuscripts are submitted by authors, and if they're published, then the author gets paid, and you can be a writer and you can make a living this way. In scientific publishing, the manuscripts are all provided for free. They are reviewed by peer experts, usually professors or experts in the topics, and those people are not paid. Then the results from review come back to the editors, and the editors decide whether or not to publish an article based on the feedback. The money is all made by the journal publisher, who charges libraries for the subscription to the journal. People don't, they're not like magazines where you buy it in your home. I mean, these are things that are subscribed to almost always just by libraries. And you may know that journals are rated by impact factors, and the impact factor is defined as follows. This is from a Wikipedia entry that I accessed when I first prepared this lecture for one of my classes. So if a journal has an impact factor of 3, then that means that the papers published in 2006 and 2007 received on average 3 citations each in 2008. So the impact factor of 3 applies to the year 2008. So you would like to publish in a journal which has a high impact factor, because that means the papers in that journal are very important. How do you know they're important? They're important because people cite them in their own papers, okay? And the reason I'm going over all of this is that if you're writing a paper, then it's good for you to know something about the journals where the papers appear, because that's what will determine whether or not your paper gets published. Okay. So if you've looked in a journal before, you know that it's very common for there to be what I call regular research papers, so just a description of a research result. Sometimes you have a rapid communication. Rapid means that it's published a little bit more quickly, so perhaps the review could happen in just a week instead of a month or two. Letters are usually something brief. A note might be something which is just a relatively small contribution, not a full paper, maybe makes just a relatively minor point, but still worth publishing. Some journals publish notes, some do not. The most heavily cited papers tend to be review articles, which are useful if you're a student or even anyone, and a scientist wanting to learn something about a new field, new to you, and you want to know something about it. A very good strategy is to start by collecting some review articles and reading them. These are not disclosures of new research results. These are collections. It's a summary of the results of other people's research, but it allows you to become knowledgeable about a field very quickly without reading all the original papers. So if you've ever looked at a scientific paper, you know that they have they vary depending upon what the journal is, but there's a structure that's often very much like this. So you have an abstract, which is maybe a paragraph, maybe 200 words. Sometimes it's limited to 200 or 300 words, just describing the main results of the research. There'll almost always be an introduction section and some background reading. It's important for papers that are experimental to describe the experimental techniques that are used. If a paper is maybe computational, then you describe the computational methods that are used. The main body of the paper is the description of the results and the discussion. Sometimes the results and discussion will be combined into one section. Sometimes a journal will require that you present the results separately from the discussion. The results are what you observed, and the discussion is what you think that those results mean. That's how they're different. There's usually a conclusion section, acknowledgements. You will cite some references. Sometimes there'll be a section where you acknowledge the funding source. Sometimes a journal will ask a description of the contributions of each individual author to a particular paper. So a few other smaller things, but these are the main things. And if you look in a paper, and many of you probably have looked in papers before, then you know that a paper will have figures. Figure always has a caption. So there'll be a graph or maybe a bar, something, a graphical, and there's a caption which describes what that is. A table always has a title. It's always got rows and columns, and you've got a title for each row and each column. If you're in chemistry, then you sometimes might use a chart to illustrate a complex experiment. Sometimes it's helpful to draw a particular experiment or something you're trying to illustrate. And a scheme is usually specifically means a synthetic reaction. So you use a reaction scheme. If you're writing a paper on a chemical synthesis, then you might use chemical drawings to describe that reaction. So these are all part of at least in chemistry, these are part of scientific papers. And it's very common now, was not when I began publishing, but it's very common now to have supplemental or supporting materials, which are not published with the paper. So if you download a copy of a paper, you don't get the supporting materials, but you can go online and get them. And often there'll be very large tables or data sets that you don't necessarily want to appear in the paper, but you do want people to have access to. So if a paper is too long, an editor will often say, well, take part of that material and put it in the supporting material. Decide what's not very important and put that in the supplemental or supporting material. So that's a common element now of many scientific papers. So I've got really just 3 slides or so here on actually writing papers. And I take some advice from this paper right here, written by George Whitesides. My understanding of this paper is that Dr. Whitesides, who you may know is a very famous chemistry professor from Harvard, has written many, many hundreds of papers, has a very large research group, even now. He's been long emeritus, but he still is active. And he, many years ago, wrote a description for his own research group on his advice to them on how to write a paper. And he had so many people ask him could you give me a copy of that he decided to publish his advice to people for writing papers? And this is where you can find this advice. And so Dr. Whitesides is a big proponent of using an outline. Okay, so if you're going to write a paper, you don't just sit down and write the title and the abstract and the introduction. It does not make sense to go linearly from the beginning to the end. It's good to have an outline which covers the topics and it reviews what the data for the paper is going to be. And one of Dr. Whiteside's points here is that the outline really could be written, the outline for a paper could be written at the start of a research project. You don't necessarily write the outline just when you're ready to write the paper. The outline is really a guide for you as you do your research. So as you maybe do experiments, or if you're not doing experiments, you're doing modeling, or whatever you're doing, as you're doing research, you're getting results that you eventually want to publish. As those results accumulate, it may be that the outline for your paper changes. You may find some things that are unexpected. Some of the things that you expected to confirm maybe are not confirmed. That's okay. That's why we do the research, because we want to find out. But if you have an outline, so people often don't think about how they're going to write the paper until they have enough research done to write a paper. And Dr. Whiteside's point is you should write the outline at the start of the project. So that's one of his points. As you prepare an outline, you should ask yourself some important questions. So the most important question is, why did you do this work? Okay, what are you trying to show? What are you trying to do? When you're done, you can look back on why you did this work. When you're starting, you could think about why you are going to do this work. Is there a hypothesis that you're testing? Some of you may have written grant proposals. If you're like me, you've had grant proposals declined before. And one of the very common things that a grant proposal reviewer would say on a proposal is, well, they never really put in a hypothesis. And so this is just a description of a bunch of experiments. It's not really testing a hypothesis. Okay, it's always bad to read that result because it means that your proposal was not funded. And so it's the same true as of a paper. You know, it's easier to write a paper if you are testing a hypothesis, and it's easiest to test a hypothesis if you write that hypothesis before you start the research. Okay, so you could think about what you meant to test. If you've already done the research, well, did you actually test the hypothesis you meant to? It's very easy to become distracted during the course of a research project. You start tracking down all these little things, and then you realize, oh, I never tested the hypothesis that I set out to test. Okay, be honest with yourself. You know, did you really test it or not? Many times you do research that doesn't test a hypothesis. That's okay. It's just good to know, and maybe you can change, or maybe you have a different hypothesis. You always want to think before you get ready to sit down and write a paper, well, what did you do? Okay. You think you know what you did, but when you go to sit down and write, then you have to really think about what you did. If you're doing synthesis, what compounds did you make? If you're doing measurements, what measurements did you make? If you're running simulations, what simulations did you run? And then once you are really clear on what you did, then you want to know, what did you learn from what you did? And then the combination of all of these things will help you to answer the most important question of all that you should be able to answer before you start to write a paper. And that is, what do you want to say? Don't start writing a paper until, if there's one piece of advice that I would ask you to remember, if you forget everything else that I said this morning, you should remember, when you write a paper, you do it because you have something that you want to say. Okay. And you have to know what that thing is before you go to start the paper. So this is Dr. Whiteside's advice, and I have found this advice to be very valuable in the course of my career. So if I'm working with a student and we're going to write a paper, this is kind of the sequence of steps that I will often ask a student to follow. I think it's useful to write a title first. You may change this title later on, but it's good to think about, well, what would the title of it be? Because when you write a title, It means you've thought a little bit about what your story is. What are you trying to say? So you write a title, and then I always tell the students to create the figures. It's not the first thing, but the second thing. Draw the graphs, draw the figures. If it's a synthesis, draw the chemical reaction sequences. If it's an electrochemical experiment, then maybe you make the voltammograms, or maybe you put the Tafel plots, or all the various things that you need. Create those figures as one of the very first things you do. Sometimes you're going to present your results as data tables. Make the data tables before you really start writing any text. You want to have all that stuff done before you write any text. Once you've got all the figures and the data tables in line, and of course you can change them. You can always change them. You can always add some, you can combine them, but you want to have at least a first set ready before you start to write. Then I often ask people to write the experimental section first, because that's relatively easy. What did you do? If you did a certain set of measurements, you describe those measurements. If you did a synthesis, you describe the synthesis. After the experimental section is written, and the standard for writing an experimental section of a paper is that a person who is reasonably knowledgeable in the field should be able to read that experimental section of a paper and reproduce the results that you obtained in a laboratory. That's the standard. It has to be able to be reproduced. You can assume that a person knows just general things about your field, whether it's chemistry or physics, whatever it is. So you don't have to describe every single little thing, but it has to be enough that a reasonably knowledgeable person could go back and reproduce the results. If the results are very important and they're very new, you can bet somebody's going to do that. They're going to go and try to reproduce them. So you have to write enough to be able to reproduce them. So then the results and discussion. This is where you want to know, what are you trying to say? Tell your story here. And for beginning writers, I often tell them to just write to the figures. Okay, you say, oh, in figure 1, we see da 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 da, and you just say what figure 1 says. Figure 2 shows that, da, da, da. Table 1 shows that, and just it's a very simplistic way of writing, but it's a good way to start because it makes sure that you hit all the points that you need to hit. Then I tell people to write the introduction. You don't want to write the introduction as the first thing because you don't really know yet what you're introducing. This is a very common thing for people that are writing, is they write the introduction first. It ends up being 7 pages long. It's too long. Then they write the rest of the paper, and then they realize that 3/4 of the introduction actually has nothing to do with their paper. It's just stuff that they wrote that made them feel better. And we're kind of brainstorming a little bit while they did it. And then 3/4 of that introduction gets cut out. And so it's better to just write it after you know what you're writing. Very famous electrochemist Al Bard used to be the editor of the Journal of the American Chemical Society, and Dr. Bard used to tell his students that an introduction section to a paper should be no more than 3 or 4 paragraphs. That's it. If you're writing more than that in the introduction, you're just writing it for yourself. Okay? It should be relatively short. Then you write the conclusion, and then the last thing you write is the first thing that you would read, which is the abstract. So then you're done, except of course you have to look at everything. Every good paper takes many, many, many revisions. I like to save the files by number, so I'll have something about the paper, and then I'll say version 1, and then the next version will be version 2. And let me see here. Yeah, okay, we're doing plenty on time. And then often by the time I go to submit, I'm maybe up to version 20 or 25. So I do many, 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 many versions. And so you should not think that just because you've finished all the parts that the paper's ready to submit. You should most certainly share with other people, have other people read it, get a lot of good critiques, ask these questions that I've written down. I haven't yet spoken about what journal you would be writing to. At some point along this process, sometimes I know here at step 0, I know exactly what journal I'm writing to. Increasingly, I'm coming to believe that you should decide what journal you're going to submit to before you start writing. Sometimes people start writing and then they change, what their idea is, what the journal is. I'll say more about matching the journal's requirements in a moment. One of the last things you do if you're submitting this paper to a journal is you have to recommend reviewers. And so you and your co-authors will sit down and think about who would be good reviewers for your paper. You have to write a cover letter. I'm a journal editor now. So whenever a paper comes into the journal, I read the cover letter. What's in the cover letter? The author tells me why this paper is significant. Why is it important? Okay. Usually it's just one page or sometimes one or two pages, but it's not necessarily, it's not the paper, but it's the author's description of why this paper is important. And that's a useful thing for an editor to know. So that's the process. Speaking of journals, once you choose what journal you're going to write to, every journal has some kind of a instructions for authors, a guide for authors. And you should look very closely at the guide for authors to make sure that you are writing the paper in the way that the journal expects you to write it. If you write a paper that does not follow the instructions from the journal, then they will often return it without review. So you have to write according to the instructions. And it's, there are some common elements. Almost every journal will have an experimental section and the articles will have a results and discussion, but there are a lot of differences as well. And I won't try to take time and explain the differences among different journals, but I just tell you that you should, at a very early stage, get a copy of the instructions for authors and read it and make sure that you're incorporating the ideas that are in that instruction document into your writing, that you're writing it in the way that the journal has requested. So, you know, just I've said a couple of times that when you're going to write a paper, you should know what you want to say. A paper that reads very well is a paper that tells a story. I often tell students that if they're getting ready to write a paper, they should know what the story is that they want to tell. If they're just writing results because they have a big pile of results and you feel like it's time to write them up and you don't have a story, then the writing will be very difficult because you don't really know what you want to say. You want to know what you want to say before you go to write. So you want to know what you want to say. Then once you know what you want to say, then it should be very easy. You just say what you want to say. Okay, your paper will read very well. It will be very impactful if you know what you want to say and then you just say it. It's good to keep it simple, but of course it can be too simple. A paper has to be simple, but it also has to be accurate and it has to be thorough. And sometimes the concepts that you're discussing, your story might have some complexity to it. You have to tell the story, even if it's complex, but try to keep it as simple as possible. Your readers will appreciate that. I often tell writers to write to the pictures, write to the figures, make sure that your writing refers to the figures. You should never have figures in a paper that you don't refer to in the text. And it's a good idea not to refer too much in the paper to figures that are not in the paper. Sometimes you have to write and you say a figure is in the supporting material. Sometimes you do that, it's okay. But if you have too much material that's in the supporting material, well, maybe you need to put that in the main body of the paper. And then the last thing I would say is that as you're writing, and it's very hard to do this sometimes because you tend to fall in love with your own writing, but it's very good to think like a reviewer because your paper will go to a reviewer. And so if you can read it and think, well, if I was a reviewer, what would I think of this? And if the answer to that question is, I would think it's not very good, then you should try to make it better. Okay, so try to put yourself in the position of a person who might receive your paper to review. And if you think like that, then you can try to answer the questions that the reviewer will have, and then your paper will have a better chance of being reviewed favorably. I'm one of the about 12 editors of the Journal of Power Sources. We have a guide for authors. It discusses all of these things, many topics here. How to submit your paper. This journal has an impact factor of about 8.25, which is one of the highest among electrochemistry journals, although it's not as high as journals like Science and Nature, Journal of the American Chemical Society, things like that. But it does pretty well for that. This journal, if you go to the webpage of this journal, it says that it's a journal for people interested in the science, the technology, and the applications of sources of electrochemical power. If you didn't know that, you might think that An internal combustion engine is a source of power. So I'm going to write a paper on an internal combustion engine and send it to the Journal of Power Sources. And I guarantee you that paper will not be published in the journal. It will not even be reviewed because it's not electrochemical power. And so you have to understand enough about the journal. Some journals are very specific, like this one. The Journal of Power Sources is pretty specific in terms of what kinds of papers it takes. Other journals, the Journal of the American Chemical Society, well, it's just got to be good chemistry. Could be a little bit more general. The journal Science, sometimes called a magazine, really, because it's a combination of some science articles and other types of general interest articles. You know, it's just anything having to do with science. You can go from very broad to very specific. And there's a list here of the types of topics that are normally considered in the Journal of Power Sources. It's good for you to be aware of that when you're deciding whether or not to send a paper to the Journal of Power Sources. About 2 years ago, the editors, before I was an editor actually, so I'm not a co-author on any of these papers, they did a very nice thing for potential authors of the Journal of Power Sources papers, is they published a guide for good practice when writing papers on different topics. So there's a paper here, and you can find it in the journal, and it's good reading. So if you're considering writing a paper on fuel cells or electrolysis cells, this paper will tell you what should be in your paper and what is not of interest. And so there are specific things that they've just been studied so much that the editors have decided, well, we're not going to publish things that are on this topic anymore. It's good if you know that ahead of time, then you can write your paper and send it to some other journal, not this journal. So for example, right here, I have done this myself. People send in papers on new catalysts for fuel cells. That's great. It's wonderful to have a new catalyst for a fuel cell. But if you don't make a fuel cell out of it, then it should go to another journal where people study catalyst properties and not fuel cells. So it has to be used in a fuel cell. So there's some advice here. There's a similar paper on batteries. So again, if you have a material that's a new material for a battery, you have to have actually made a battery and tested a battery. And there's some very, specific tests that have to be done on a battery. And some capacitors, other types of electrochemical power sources. So some journals have something like this. I just saw today that there's actually a detailed description, 2-page description in the journal Joule on all the requirements that they have for a paper on batteries. Okay, it's a 2-page checklist. You have to have all these things in your paper. If you don't have all those things, you're not sending it to the journal Joule. They won't review it. So it's good to know those things before you go to write a paper. I have some brief sort of advice on reading of scientific papers. There we go. This is mostly about writing, but another thing that we do with scientific papers is reading them. So you can read papers, you could read them for a lot of different reasons. Maybe it was assigned, maybe you're looking for something specific, maybe you're just interested. There are a lot of ways to read a paper, just like there are a lot of ways to read a book. You can sit down and read the whole thing, cover to cover. You can just look for the part that you want. You can study specific parts. There's no rule that says you have to read an entire paper cover to cover. You can just sort of pick and choose what you want to read. And this is just general good work habits here. I've done this trying to read papers before. I've tried to read papers sometimes on airplanes, sometimes when I'm driving or when my wife is driving and I'm in the car. It's hard to read papers in those kind of conditions with me. It's too many distractions. Maybe some of you have better luck with that. But for me, it's just good to set aside time and be quiet and have there be no distractions. And you want to read with a goal. If you don't read with a goal, then you just get stuck. You just read the same thing over and over. This is a brief paper, which I think I won't really go over very much here. It's this fellow who's a computer scientist, says you can use this method for reading papers. You read initially very fast, just scan very quickly, just to get a sense of what the paper's about. You're deciding at this point, do you want to really read this paper in depth or not? And then, you could maybe have a second pass where you look a little bit closer, maybe take a half an hour to an hour to read the paper. I've read so many papers over the years, I can do these a little quicker, but if I take 20 minutes with a paper, that's a long time. And then if I really, really have to understand deeply then a paper, there's just no getting around this. If there's some papers that are so important to your field that you need to study them very, very carefully, then you need to take many hours and read that paper very, very carefully. If you take many hours to read every paper that you ever read, you will not read very many papers. So this is why you have to kind of be careful about how you read. Sometimes you read just for one or two things, and sometimes you read very closely. Just the closing thoughts here on writing. You know, it's always fun to do research in the laboratory, especially when things are working very well. But you know, your fun results that you obtain in the laboratory are not really official until you've written them up. So you have to, you know, good scientists always have that instinct to take their results and write them. Some of you maybe are going to work on a master's thesis or doctoral dissertation. I've talked a lot about writing for journal articles, but you know, this kind of writing is, this advice is also very useful for a dissertation or a thesis. And then the last point I would just say is that if you're thinking of a career in science, then the ability to write well is very important. It has to do a lot with, you know, how your work is going to be perceived. And how successful you might be. I haven't talked today about grant proposal writing, but that's another type of scientific writing that's very important to the success of young scientists. So it's good to be able to write a good grant proposal. And so if any time you invest in learning to be a good writer is going to be time very well invested for yourself. So that's the last thoughts I had. I think I've got a few slides here that I'll go through very quickly on the College of Science because I know we're running out of time. The Clemson College of Science has these 5 departments. There's sort of a, we've got these 5 pillars of discovery, we call them. So these are not our departments, but we've got research in genetics and precision medicine, health innovation, advanced materials, data and information science, and astrophysical and planetary science. These are all described in a strategic plan that we have. I was playing with this Venn diagram and it gives me an interesting way of sort of categorizing some of our research. So we've got some things that are obviously just pure physical science, things like astronomy and chemistry, things that are pure life science, things like genetics and agriculture, organismal biology, microbiology, things that are pure mathematical and statistical science. We have a big group working on cybersecurity and something called blockchain. It's involved in cryptocurrency. Data science and analytics. These are all things that are clearly mathematical and statistical sciences. And there are some things that cross the boundaries, like measurement science. I'm an analytical chemist. A lot of analytical chemists are working very closely with life scientists. Other analytical chemists work very closely with physical scientists. There's a whole emerging field of imaging science. All the important imaging problems, many of the important imaging problems are in life science, even though the techniques used for imaging are physical science techniques. The fields of biochemistry and biophysics have in their names that they bridge between physical and life sciences. There's a couple of emerging new fields now, quantum computing, maybe you've heard of this. It involves some new physical materials and quantum phenomena that can be used in ways that can allow computing that's a little different than the type of computing that maybe has been popular for the last 50 or 100 years. You know, using binary numbers and the types of computing devices that we have now. Bioinformatics is an exploding new field that takes advantage of advances in mathematics and computational science applied to fields of life sciences that have really, really large data sets like genetic sequencing. And then right in the center of it all is computational modeling, which can be used really for almost anything. So this is a nice way to think about science. This is our college. We've got a little over 250 faculty, a little over 2,600 undergraduate students, a little over 600 graduate students across all 5 departments. We've got some centers that I won't spend much time with. Dr. Rao is one of your speakers in this symposium. He's gonna, I think, talk later. I guess you can guess from this picture that he works with graphene. So that's a picture, a model of graphene. We've got some centers here. These are some of our faculty awards. I won't spend much time on these. We've got NSF Career Award winners. We've got NIH grant winners. If you're interested in graduate study in any of these programs, then there's the URL. The easiest thing to do is just, put in a Google search or an online search for Clemson and graduate study in College of Science or whatever the department is you're interested in, and be happy to receive an application. So that's all I have. And thank you for your attention. Thanks again for the invitation. And thanks for this opportunity to share with you some of my thoughts on scientific writing. So thank you.
Thank you very much, sir. May I request Professor P.V. Anbuli, sir, to take the charge and ask the few questions of you, as well as a few participants have put their questions in the chat box. So may I request Professor P.V. Anbuli, sir?
Yes, sir. Yes, sir. Yes.
Professor Anbuli, sir, is working in Department of Chemistry as a professor, and he is outstanding researcher. Especially, he is working in organic synthesis. Sir, Anbuli, sir, please take charge.
Yes, sir. Yes, sir. Yes. First of all, I am very much thankful to Professor Stephen, sir, for his valuable time. And I request one or two audience, if they have any questions, please ask him.
Sir, in the chat box, there are few questions.
Okay.
Anbuli, sir.
Okay. I will check.
Okay.
Stephen, sir. Hello.
Yes, go ahead.
One of our student asking how will get admission in USA for PhD.
Yes. So you apply. It's helpful to I was when I was in charge of graduate admissions in chemistry, I would always say that the most important thing is to have some research experience. Okay, so you want to have research experience. So for students who want to come for graduate study, if you've done an undergraduate program, the equivalent of an undergraduate program, it's helpful to have some research experience. If you have publications, then that's very good. It's right. It's difficult now with international things, right? There are visa issues that are still being worked out. Hopefully, those are going to get better over the coming years. It helps a lot to have a connection with a professor in the institution. So sometimes you reach out, and if you establish a connection, that's helpful. It's always helpful if a person has some financial support they're bringing with them. I know that's very uncommon, very hard to get. People have that. Of course, that's always a very attractive thing. And so then, the good grades, and if you're making contact with an individual professor, then it's good that if you're show that you are familiar with what that professor does, and you maybe think about you want to talk about how what you want to do in your graduate program would be a good match to that professor. That's the best advice I can give. I know it's hard to. There are many applicants, and not everybody gets in. So I don't want to make you think that I could promise that anybody would get in. But those are the things that usually make a difference to an admissions committee.
Thank you very much, sir.
Sir, I have one question. Anbuli, sir, can I ask?
Yes, sir. Yes.
Sir, hello.
Yes.
Professor Stephen, already you highlighted the few aspects about the how to write a research article. Then during a research article writing, my question is that which type of tenses we want to use?
Tenses.
Whether we want to use present tense or past tense in research article writing. Yeah.
So the traditional rule there is to use so if it's so there are tenses, there are present tense and past tense. It's often past tense when describing experiments that you have done.
Yeah, okay.
But you might use present tense to describe results that are findings.
Okay.
We believe that something is true. That's a present tense. You believe that now.
Yeah.
You believe that now. But if you did an experiment, well, you did that experiment in the past. And so you would describe that with a past tense.
And
it used to be that people would discourage the use of a personal type of writing, like we or I. They would say, don't do that. You try to write in such a way that you don't have to phrase it that way. That's becoming a little bit less of of a rule now. So you see many people will use we, we investigated this, instead of saying something like this subject was investigated, because it's just cumbersome in the writing. If you never ever use I or we, or it becomes difficult to write.
Yes. Thank you very much, sir. Sir,
Yes.
I like to ask one question from my side.
Yes.
Yes, may I ask?
Yes.
Sir, if there is a good experimental results, but paper writing is poor, can we get a good publication? If we have a good extraordinary experimental results, but paper writing is poor, can we get a good publication? Or this is a
Well, so if the question is if can you get published with poor writing? I mean, there are papers published that have poor writing for sure. It depends on the journal. I mean, a very good journal will never publish that. There are journals that would certainly publish it. You usually want to try. Usually, an author tries to get a journal which has a good impact factor, which people will read. And if you want to impress reviewers and such a journal, then you would want the writing to be good. It's very easy to make good experimental results not look so good by not having good writing to go along with it. I would say that it's you can get anything published. It just depends where you're willing to send it. But if you want to send it to a good journal, I think that it's worth doing good writing.
You mean that to get a publication in good reputed international journals, it is a combination of good experimental results and scientific writing?
The world is filled with very, very good experimental results that were written up poorly, that nobody ever read because they couldn't understand the writing, and so
yes,
it didn't have any impact. That's very common.
Yes. Now, Professor Delekar, sir, let me conclude with vote of thanks.
Yeah, you conclude. Okay, at the end.
Sir, on behalf of Organizing Committee, Department of Chemistry, Shivaji University, Kolhapur, Maharashtra, India, I like to express our special thanks to Professor Stephen Krieger, sir, for his valuable time. Really, sir, you made our morning scientific by your scientific story on writing research papers. You covered all the points from types of research papers to how to read the research papers. I am confident that your talk will be very useful for our research students in their career. Once again, we are very much thankful for your valuable time on a writing research papers, and hope in future, after situation is normal, we will meet in India, specifically in our Shivaji University, Kolhapur, in 2022. Good. Thank you once again, sir. I also thankful to Dr. Dilip for his valuable support to Professor Delekar, sir, to conduct this lecture series. And I am also thankful to all the participants for their patience listening and their valuable time. And I like to conclude that this session is over, and have a nice day. Thank you, one and all.
Okay, thank you, sir. Thank you. Okay, thank you. Okay, Professor Stephen. Thank you. Okay, Dr. Dilip, and okay, thanks. Okay, to Professor Anbule sir for conducting this session very smoothly. Thanks to all the participants as well. Okay, bye. See you.
Thank you, sir.
Okay.
Thank you.